Good afternoon, good morning to everybody joining us for another episode of Takeo Tuesday. Glad you can all join us today. My name is Dave Holdorf with Takeo. Joined with me also, I do have John Barba, and I also have Rick Mayo. So for those of you that were with me, I guess 2 weeks ago, I think I ran the show a little solo since John was out and Rick was out traveling. So we got the whole crew back again today. So that is awesome. I am so excited to be working with these two gentlemen again. I felt like I was all alone on an island for a couple of days. I don't know. Wait a minute. That was you, John. You were on an island, but not alone.
I
So
was on an island. It wasn't a tropical island. It was the
right.
British island, the United Kingdom. I didn't.
Yes.
I was there so long. I think I developed an accent.
Oh yeah. Okay. Awesome. Awesome. Good to hear. Good to hear. So welcome to another residential focused Takeo Tuesday, and today's class is going to be ECM circulators versus PSC, or permanent split capacitor, or our standard efficiency circulators. And we're going to be going through a couple of different applications, so to speak, and looking at the pump curves and what's going on with those circulators. So that's the focus of today. So with that being said, let's get this thing started. So the first thing is go to webinar, your control panel, just to make sure that you can see and hear and be part of the program with us. If you happen to notice this orange arrow and it is pointing to the left, I want you to click on it and it will expand it out to as what you see here on the screen. And what you'll end up with is your audio section. Now your microphones are all are muted, but you have your speaker selection just to want to make sure that you can hear us, and you can choose the different speakers that you may have connected to your computer. There will be handouts. There is one handout included today. It's just our Takeo catalog. So if you want to review and take a look at the different ECM circulators that we have, that is listed there. And then the next section is our questions and chat area. And this is how you will communicate with us. So I will be doing the presentation this day. John and Rick will be monitoring the questions, so you can always ask any questions at any time, at any point during the presentation. We do not save them for the end because you'll forget the questions when you get to the end. So ask it immediately, whether it's something that you saw on the screen 5 slides ago, whether it's something that's on the screen currently, and if you're really, really good, the next slide. If you have a question on the next slide, all right. So
right.
I want you to be able to ask us that way and answer questions too. You know, I may throw out some really simple questions, and the idea behind that is to make sure that you're still connected, and that I'm still connected too, because there have been times, as we all know, the internet isn't perfect always, where we may be talking to ourselves and not to you all. So, at that point right now, just to make sure I know everybody can communicate with us, if you could just do a quick hi, hello, how are you? That would be wonderful to make sure everything is working. And I see Brian and Jake dropping something in there, and Ryan and Dave, Mike Larson, excellent. All right, hi, hello. There we go. Stephen Pritchard got it perfectly. Hi, hello, how are you? I love it when they actually hear the instructions coming. And Stephen, you've been here a few times before. You know how it all works. So that is perfect tonight. Today, I'm sorry. It is not nighttime, so that is perfect. Thank you very much, everybody. And if you are using a device, things will look a little bit different. The first thing is you would have to toggle between the cameras and the presentation, so you'll have to slide back and forth. You would notice a second bubble sitting right here for the presentation. Your audio settings is the next section there, and that's where you're going to move around, obviously, to where you can hear us from. And then your questions to ask. Now, if handouts are a little bit different to find on each device, but you should be able to get the handout if you're looking at it on a phone or your tablet. So, and then also to answer questions, you'll have to jump away from the presentation to ask the question or to answer any of the questions. So, all righty. So as we are getting ready to go, if there's any questions, like I said, make sure you put them in there immediately, and John and Rick will answer, or they will interrupt me, and we will tackle that question together. So please do make sure I'm not the only person talking today. Otherwise, listening to the New Yorker drone on just gets a little boring some days. And the questions slow me down a little bit. I tend to talk a little fast during our presentations. So with that being said, let's take a look at our circulator curves, our performance curves with our PSC or standard efficiency circulators. All right, so that's where I want to really start off first, is looking at our standard PSC design circulators. And what you look at here is all of the 00 circulators performance curves that we have. So everything from the 003 all the way up to the 0014. So this is your standard efficiency going from a 1/40th horsepower up to your 1/6 horsepower. And a little bit of history about the naming system here. All right, the 00 naming system with the circulators, there is none. All right, it was whatever we developed, that, and whatever number was next is what it got. Yes, it started with the 007 back in 1950. In 1970, I'm sorry, in around 1970, 1971, we introduced the 007. That one got its name based upon, what do you think, everybody? And I know what you're thinking, and you're 85% true. Why it is called the 007. And yes, Valerie, perfect. Our product manager, and we have that confirmed about 85% at the time. That was the product name that the project name in-house was the 007, related to James Bond. He was a big James Bond fan, and the name just stuck. So from there on out, it was just whatever number was next. As we started off with some rhyme or reason. But you can see here, there's a lot of different circulators that cover off on the standard efficiency PSC style motors. Now, our focus today is going to be on the residential side. So let's zoom in a little bit, because it's very rare are we going to need a 0013 that can do up to 34 foot ahead and 34 gallons a minute in a residential setting. If you need that much pump in a house, you're not in a house. All right, you're looking at more. Yeah, it might be the 15,000 square foot McMansion going on with only 2 people living in it, but that's commercial work, right? So let's zoom in a little bit and focus on, say, from the 008 and down in our single speed standard AC efficiency circulators themselves. And so now it looks a little closer. You could see our flow across the bottom of the screen and our head on the left-hand side of the screen and our different model numbers. These are not the circulator numbers, these are the model numbers. Now, a couple of weeks ago, maybe about a month ago, we had done a Takeo Tuesday class on pump curves and system curves and where they operate. So I'm not going to go through that math that John had covered off. If anybody is interested or needs or missed that class and you really need the link to it, we can easily send that to you. So if you need the link to that previous Takeo Tuesday class, let us know in the questions and we'll make sure we get that link shared out to everybody. So, but I'm going to use a couple of numbers. And let's say we had a system that was looking for just under 7 gallons a minute at about 5 foot ahead. So X marks our spot. And now what you need to do is choose a circulator to fulfill your needs. And we see we have several different selection points. So we can start off with the 006 cast iron circulator on pump curve number 3. So, but we don't find many of those in the wild. We see more often the 006B circulators, but we use those more often in our DHW recirc applications. So they tend to cost a little bit more because of the construction materials used. The 005, the next curve up on curve 2, is probably a pretty good choice. The 007 is probably used about 80% of that time, and we can see the 008 would also work. But as we start getting further away from our design point, is where we start losing the efficiency, or we start over pumping our system itself. And as we see in today's trend, we see our zones getting smaller and smaller, or seeing more and more zones in people's homes with small zones. You could see where easily down here at the 3 gallons a minute, 5 foot ahead range fits a lot of different circulators. And therefore our standard size circs that we picked before might be way too large for our applications, creating other challenges in our system. So, but what about 3-speeds? All right, and pulling up those 3-speed pump curves. I mean, we've been told many, many years that 3-speeds are awesome circulators, that we have, you know, it's the one size fits all type of circulator. So we have lots of options with them. Hey, it's got a selection switch on there, right? And as you can see here in the middle of the screen, it's got low, it's got medium, and it's got no callback speed. Yes, called high. All right, and how many times are they set on low and medium? If you've done any service work or gone out to job sites in the past, where would you see that speed? You know, what selection is usually set up? Or if you use a 3-speed circulator, what speed do you set it in, and for what reasons, if you have some answers out there? So let us know on where you normally see them, and or how do you know which curve to set them up for? So let's take a look at those pump curves. Whoops, sorry, wrong button here. There we go. And residentially, we see the 0015 MSF3 as the more common 3-speed circulator. We do also offer the 0010. The 0010 3-speed circulator is a great replacement circulator for your older projects that had that Takeo 110, the Red Baron circulator, or your B&G 100. Really good selection for that if you needed what that circulator did. All right. But your 0015 is our more common sized circulator, which also follows suit to a lot of other brands out there that also have a 3-speed selection switch on there. So your low, medium, and high settings you see on the blue curves. And if we were to compare it up to our just under 7 gallons a minute, 5 foot ahead, you'll notice that we're just over low speed, just over low. And we probably have a little bit of extra thrown into our calculation here on our head calculation when we had done them. So we probably could run it at low, but medium would give us the safe. If this number was accurate, would give us the number, but high probably wouldn't be needed. Now, whether this is zone valves or zone pumps doesn't really make a difference. This is what the total demand is. And as we start seeing smaller and smaller zones in our projects, a lot of times we can easily set them up at low speed. So, but you have just that choice, that low, medium, and high settings on there. So the big conversation comes into play on why ECM, why change? I mean, the 007 was our first AC standard efficiency circulator back in 1971. So that circulator is over 50 years old already. So why would we want to change the technology in circulators? For really, it comes down to not why ECM, it comes into why not. All right, it's one of those things where we can start adding technology into circulators. It hasn't changed a lot in 50 years. Other than ECM circulators over the last 50 years, what other technological advancement have we made to circulators out there? So counting the 007 as one of the first residential wet rotor circulators brought into the market, what other technological advancement have you seen in circulators? All right. Love to see some of your comments that are out there when it comes to what other advancements have we made in the world of residential circs. So one of the things about adding ECM or making these circulators variable speed is that we can start adding to system efficiency that's out there. All right, we want to make the system more efficient. It's not just about component efficiency, it's also about system efficiencies, and circulators have such a large role in how our systems operate, not just in component to component efficiency, but let's make the system do what it's supposed to do, and 2, give us the efficiency that we're looking for, making sure that we have 1, the proper flow going through our boilers for the heat transfer to occur there, but 2, make sure we have enough flow out to the residential side, and 1, not be under pumping and or over pumping. All right, we end up having to over pump quite a few projects out there, but if we didn't have to, can we drop it down? And the other big conversation that comes into play is electrical savings. Yes, there is electrical savings when we see ECM circulators out there. And if you read the brochures on any of the ECM circs that we have, and as well as everybody else out there, you read the front side of the brochure, what I like to call the warm and fuzzy side of it, it says up to 85% electrical savings. That can be a big deal. And there is going to be a time and date out there when we're not going to be able to manufacture standard efficiency. A couple of years ago, 1 horsepower and above had to meet certain efficiency standards based upon the DOE. We can see that happening on 1 on 1 horsepower and below in the near future. Okay, so we will see that coming, where we're not the standard fixed speed or standard efficiency circulators are not going to be able to manufacture it anymore. When we look at standard efficiency wire to water transfer, meaning how much electricity is needed in order to move water, we look at about 27% efficiency. 27% of the electricity that goes into our circulator is used to move water. Now, when we jump into the ECM range, we're in the 50s, all right? And it changes based upon which model that we have, but we get into the 50 range with wire to water efficiencies. So in essence, we're practically doubling our efficiencies that we can get out of it. All right, so what is ECM? All right, ECM stands for electronically commutated motor. What does that mean? All right, what that means is it's not a requirement by DOE that we have to manufacture to ECM. We just have to get to a higher efficiency, and ECM is a way for us to get there. It's just that it's a means to get that higher wire to water efficiency out of the circulator. But what ECM also brings us is a lot of controllability out of that circulator, meaning that we can easily change the speed by just changing the voltage and changing the way the poles are created, so we can drop the speed. We look at a standard efficiency circulator, we're looking at 3450 RPM or 1725. All right, most of our wet rotor circs are actually not most of them, all of our wet rotor circs are running at 3450 RPM. When we get into some of our inline circulators, then we can drop the RPMs to 1725, depending upon applications that we're looking for. All right, but now when we get to ECM, we can easily change the speed and we get a lot of functionality out of it because we're looking at a lot more electronics that we can drop into that circulator. So when we just look at the manufacturing of an ECM circulator, for example, so here's my standard 007E ECM part of it. When you look at it from the side, this black part that you have here in the camera, that is your motor. That is the entire motor. The green part here has our circuit board in here, and then the circuit board is mounted on top. Now I do have the motor separated here, so here we can see the motor, and right here are some terminal points where our circuit board lands on top of here and then creates the poles in order to make our circulator turn. So right out of the box, this circulator maximum power draw is looking at 44 watts. The standard AC equivalent, our PSC equivalent 007, is pulling 80 watts. So we're just about half the power running full speed. Now these all become variable speed depending upon our applications, and we're going to run a lot slower of a speed to match the demands of the system itself. So the other thing that helps us get our wire to water efficiency is that an ECM circulator has a permanent magnet built in the cartridge design, rather than creating that electromagnet and using electricity to make this magnet in the middle here on our cartridge in the rotor part. It already is a magnet. All right, so that is one of those things about it. All right, so when it comes to varying speeds, there are a couple of different ways that we can vary the speed of that circulator. All right, and the first way is by pressure differential. And a pressure differential circulator means as the pressure changes in the system, the circulator is going to follow suit. Now, in a pressure differential system, if you do have the pressure changing, it really only happens in 2 applications, in 2 installation methods that we're going to do out of our 3 that we would see. The first one is it's going to be a zone valve closing. If a zone valve closes, very high pressure differential up against that zone valve. So therefore the circulator slows down. Zone valve opens up, the pressure drops, it allows more flow to occur. So that's our first way in changing the speed of a circulator. And the second way is by temperature drop, where we're looking at external information coming into the circulator, and we're going to use a temperature sensor on the supply and on the return and change the speed of the circulator to see fit that way. So, but you don't see them in all together in one circulator. They're going to be independently. Now, a pressure differential style circulator does not read pressure whatsoever. It is not looking, there is no pressure sensors, there's no pressure transducers, there's nothing out there that's going to read pressure in the system. What an ECM delta P circulator looks for is it looks at an amp draw and an RPM. It's an algorithm. It's a calculation that is done to maintain the speed that we need the circulator to run at based upon the zones that are opening and closing, or if you had thermostatic radiator valves or proportional valves that are changing the flow characteristics of your system. So like I said, but you're not going to find them both in the same circulator. So when it comes to choosing a variable speed circulator, you need to make sure you choose the right one for the right application. The one thing and the one term that I have not used anywhere in this presentation is the word smart pumps, because I don't like that name, smart pumps. These things ain't that smart. They are not that smart. I don't want you putting this in somebody's home saying, well, I'm putting this in your house so I don't have to think. They're not that smart. All right. We still need to make sure, one, we choose the right circulator for the right application and making sure that it's the right size circulator and the right setting also. So there is no circ out there that is going to make it better for you. All right. So why use a variable speed circulator? Probably the same reason why this guy has a car on his island. All right. Because he can. All right. Actually, as we like to talk about it sometimes, and John and I stare at this thing, we think about, we would just love to see that the reason why that car is stuck in the middle of the island is because he ran out of gas there. Right. So, but why use variables? And those of you that are joined on with us today, why do you use variable speed circulator? Why have you chosen small residential circulators in some of your applications? I would love to hear some of your answers that are out there on, and if you have used them. So that would be a wonderful survey if I could find out how many people have used ECM or spec ECM circulators out there. So it is a great question out there to why have you used them in the past? All right, I see a couple answers coming in here. So ease of balancing, efficiency, energy savings. All right, so these are all excellent, excellent questions that you have there. The versatility that Robert says is great. Ease of balancing. I would love to understand what you're talking about there, Charles. Are you talking about radiant floor systems? Are you talking about panel rads or just zones that you have out in the system itself? Because when it comes to delta P circulators and trying to, I'll get to that point. Never mind. That guy says, yes, customers think I'm smart. All right, there you go. So what are they doing? They're speeding up and down as systems change. All right, as the parameters in the house changes, as the temperature outside changes. All right, there's a lot of information that can coming back to this circulator itself. So they're going to change speeds. So we talk about best applications. Is a variable speed pump good for a zone valve application or radiant floors? And I would say 90% of the times, everyone's going to say, yeah, zone valves are awesome for it, right? The circulator is going to respond as valves are opening and closing. So it speeds up and down to make sure that I don't over pump a zone and I just give close to the flow that is needed to the system itself. Radiant floor is almost the same application. All right, you put those actuators, your telestats, on a manifold, and you've got lots of different actuators that are opening and closing. However, would you use a variable speed circulator in a zone pump application? All right, so you see here in this photo, the circulator up on top is being used in variable speed because of the zone valves that we have. But then we have this one back here, all right, is not connected to zone valves. All right, so is this one varying its speed? So we see this one probably is. All right, as zone valves open and close. At this moment, we see we've got 5 zones out of the 6 that are open. All right, and this one is running, but will this one become a variable speed circ? Will it ever change speeds? And this circulator, the small 007 in the back here, its whole job is just to pump through the boiler. All right, that's its only purpose. So, would you use a variable speed pump in a zone pump application? All right, that's the question. That's the big question. But yes, the electrical savings becomes the big conversation. So let's talk about what does it cost in your boiler room for electricity? And let's say instead of those zone valves that I had on the previous screen, what if you had just straight PSC standard efficiency circulators? You had 5 007s on this project at 80 watts a piece. All right, so that means you've got a combined load of 400 watts. Now we need to convert that to kilowatts because that's what our electric bill shows us, right? We use a small number, so hopefully next month you'll use more. And now we need to know how much does the circulator actually run. And I remember starting to create these slides a few years ago, and I'm like, oh, great. I'm going to have to put data loggers on my system in my house to see how much my circulator actually runs. But I got to do it for at least 2 years because you can't just get 1 year out of it. You're going to have to get 2 years out of it. So, but then I found a chart. All right, and there was a chart that was put out by AHRI that gives us the average runtime in hours of heating systems across the United States. So for those of my friends that are a little bit north of us today, sorry I don't have that chart for up in Canada, but you could probably transpose some of those numbers up towards your neck of the woods. All right, so as you look here, this is the average runtime in hours of heating equipment across the United States here. So as in the last time I put this presentation together, I was up in Syracuse, New York. So I was hanging out right here when I used this slide last. So I do have some adjusted numbers compared to as if I was in Rhode Island or on Long Island where I am now. So as you can see up in Syracuse, this line going across here is the 2,500 hour line. In between here, this middle is looking at about 2,000 hours of runtime. All right, that's just your runtime of heating equipment, say out of a 5,000 to 6,000 hour winter. Okay, so you plug in the numbers that you know. So we had 2,500 on hours as an average. That gets us 1,000 kilowatt hours. And now, what does electricity cost in your neck of the woods? All right, and a number that I had used because of where I was, a New England average of around 17 cents a kilowatt hour, means your boiler room electrically will cost about $170 a winter. All right, a winter with 5 007s on there. So if you are really, really concerned with electrical savings, what's the easiest way to get electrical savings in your boiler room? And we should look at it, right? We're trying to design the most efficient boiler in there to use the least amount of fuel. We should also consider electrical costs too to the homeowner. It's all encompassing. Most people don't pay attention to it. They just look at the electrical as the electrical and that's it, all right? But what is it going to cost a homeowner? So if you want to save electricity, there's one easy way to save electricity. All right, and not really have to, so to speak, jump out on the ledge of new technology. All right, we go zone valves. Go zone valves in the system. So now we do 1 007 with 5 zone valves, and the zone sentries is a very low power draw zone valve at just under 1.5 watts each, and we have a total combined load of 87.2. All right, do the same math as before, and we come down to $37 a winter. All right, we saved $140. That's because we pulled out 4 pumps. All right, we pulled 4 circulators out there and we put zone valves in instead. All right, it's a very viable option. All right, obviously do the math as we have shown you in so many other classes. But now, hey, I'm still all about, I don't want to spend any more extra kilowatts. All right, so let's put in the 007E, all right, like this one here. And like I said before, this is a maximum of 44, but it goes down to a low of 4. It goes down to 4 watts of power. And when I first put one in my house, and it did have a digital readout on that to tell me the power draw. Mine ran around 12, 13 watts for most of the winter. So let's hit 20 watts as mid-road. All right, just a hair under mid-road, and do that same math. And now we're down to $42 a year with 5 ECM circulators. So obviously, what's going to be next, everybody? Let's jump in with zone valves. So we put in 1 007E, 5 zone valves, do that same math, 1,000 kilowatts divided by, get it to 0.272, 2,500 on hours, and we get down to just under $12 a winter. All right, now this is where we're really saving every last kilowatt, all right, or using it most efficiently too at the same time. So I know we've done other conversations on zone valves versus zone circulators, which one's better, the great debate on that too. So if you want to take a look at that one, that is also another Takeo Tuesday class that we have recorded and is probably on our YouTube page to find out which way is better for you and to do that math. So take a look at those. So John and Rick, I just realized I've been talking a lot over the last 30 minutes, or at least 25. Have there been any questions that have come through? I figured you would have interrupted me by now, but how we doing out there?
Everybody's doing pretty good. We've had the couple of the most interesting points that I heard from some of our viewers were why they use ECM circulators and ease of balancing. As with you, ease of balancing struck me as kind of interesting, as did match the load and also auto adapt. But we can those, I think, are worthy of discussion once you're finished. I think those would be some interesting things to share with the group once we're done with the body of the presentation.
Excellent, excellent. Thank you, John. And remember, everybody,
for those of you guys who did mention those, please stick around because we're going to have an interesting talk.
Yep, not going anywhere. We will stay online as long as you need us to cover up on your questions too. But type them in. We're not going anywhere, and we'd love to hear your comments, questions, and everything else in between. All right, so let's go take a look at some pump curves on the ECM side of things. All right, and as we jump in, the first circulator we're going to look at, and I've broken these out just so we can see them a little more clearly, is the VT2218. This is our variable speed temperature sensitive circulator, and it actually has an operating range. It doesn't have a performance curve. So what you're going to see here is at A is the minimum speed of our circulator and B is the maximum, and it will operate anywhere in between. Now, if I dare say the word smart pump again, this is probably one of the smartest ones that you can put in, as in it's going to try to find the flow that you need continuously as it warms up and cools down outside. Is going to be here. So if we go ahead and take a look at our 7 gallons a minute, 5 foot ahead, that's the curve it's going to find. All right, it's going to run that speed. So this one's a little bit larger of a circulator, runs up to 57 watts down to a low of 9. So right here, I would say under full load, design conditions, all zones running, everything, perfect alignment of the planets. You know, cats and dogs play well with each other. We're probably pulling about 30 watts on this circulator. And then if you had zones in here and zone valve closes, it would bring down to that 3 gallons a minute, 5 foot ahead. So it's always going to operate, say, in between these two curves. You know, your middle curve, that our maximum, and then there's our minimum. On startup, when everything's nice and cold, we might see it ramp up a little bit higher in order to maintain a fixed delta T. We could see some ranges that could go up and down on here, but that's what we're going to see out of the VT2218. So the 2218 has a couple of different operating modes, with 80% of them operating in the delta T mode. So, and that delta T is adjustable. We can change it between 5 and 50 degrees, but it is defaulted to 20, where we're going to find most of our operations if we're looking at, say, a regular fin tube baseboard application, or maybe some of your fan coils. But if you're doing some radiant floors where we like to operate on a 10-degree delta T, we can easily change that. Or other applications like panel rads, you can bring that out to your 30 and 40-degree delta that you like to see. So, but like I said, defaulted to a 20. Now, one of the nice things about this circulator is that we're not just stuck with delta T. We've threw the kitchen sink at this, so to speak. So what's better than a 3-speed? We have a 4-speed circulator now. So we got one more. Now you could still use your temperature sensors and it would give you a readout on what's happening, but it wouldn't become variable speed. Speed 1 is the minimum, speed 4 is maximum, and then we break the middle into 2 spots. So you have a couple of different curves. If you didn't want it to be a variable speed circulator, you can easily make it a 4-speed circ. Now we also have the option to do set point heating. So set point heating means it's going to use a temperature sensor and will speed up and down to maintain the temperature wherever that sensor is. Now we could take that sensor and put it on the water stream and read a fixed water temperature. Other applications with this temperature, as you can see, it has a wide range. I've used it in some fan coil applications where we take the temperature sensor and put it in the airstream to maintain a nice fixed air temperature coming out of the ductwork. Biggest complaint that I hear all the time with hydrocoils in your system is that we don't have warm air all the time. It starts off cold, it warms up, and then it gets too hot, and it goes up and down all the time. You take the temperature sensor and put it in the airstream and maintain a fixed air temperature. Now that would just be on a single sensor, the supply sensor, but you do have the option if you have this circulator in a non-condensing boiler, all right, your regular cast iron boiler, you take the second sensor, put it on the return side, and now we've got boiler protection so we don't drop below our condensing point, all right, so it doesn't go any slower than that. We can do some cooling with it, all right. And we can also just set it up as a straight boiler protection, say as a bypass zone, a controlled bypass across your boiler. All right, so those are the operating modes coming out of the VT2218. All right, so what about delta P? All right, our pressure differential style circulators, which we have a wide variety of in different applications, okay, and different price points that we'll see on these circulators themselves. And what I show you here is the 0018E, which has a lot of functionality out of it. And what I wanted to show you this one first, because we have derivatives of the 18 in some of its functionality, because you know, you look at the dial of this circulator here and we see 1, 2, 3, 4, 5, 6 different modes that we could put the circulator in. How many modes do you need it to operate in? You need one, right? So if you know you always do that one application, we have other circulators for you. But let's talk about the 0018 or at least delta P circulators themselves and what they have. When it comes to our delta P style circulators, we have 3 distinct operating modes and or 3 distinct applications that we're dropping them in. All right, so the first one is a zone pump application. When you set up your circulator in zone pumps, all right, we're going to set it up to give me the flow that I need. All right, we do that flow and head calculation like we showed a couple of weeks ago, and we select the circulator that gets close as we can. Well, what if you can get exactly to what you need? And instead of a 3-speed circulator where you have a couple of choices where we'll probably never need high, now we have an infinite variable speed. We can dial it into exactly what we want it to do. So that would be the right-hand part of this dial, as you can see here. And when it's running in this mode, you'll have a blue LED on our circulators. Our second application, we're looking at zone valves. All right, and zone valves, we're looking at a constant discharge pressure. So we want the circulator to become a variable speed, but also maintain the highest pressure differential that we need to send out to the system itself to satisfy the length of pipe that we have, or the pressure drop of those zones. So now it'll speed up and slow down based upon how many zones and combinations thereof that we have in the system. And in that mode, we're going to operate and have an orange LED. And then when we get to proportional pressure, all right, the third portion of the circulator itself, we're looking at thermostatic radiator valves or panel rads, any valve that we have in a system that's going to have a proportional pressure differential or change in the system. And in that mode, we're going to have a green LED that's going to light up on the circulator. So what you see here is also variable speed, but now looking at sliding instead of bopping back and forth like zone valves. It's going to slide because these valves are slowly opening and slowly closing. So let me go into some detail as we get into them. So let's take a look at a zone pump application. So if you'd like to zone by circulators out in your systems that you have out there, where do you set the dial? Where do we set it up? All right. So the dial here has a minimum setting, has a maximum, and a couple of dots in between for reference. So when you turn the dial doesn't click going going from one spot to the other. It's fluid, and wherever you stop that turn is what the speed runs. We're just giving you a couple of dots as reference points. So your minimum would be close to your 003. Your maximum is your 0015 on high. So wherever you stop, that's the speed it's going to run at. So if we bring that over to our pump curves, here you can see your 003 minimum. We see our 0015 on high, all right? And then we have the dotted lines represent the dots that are on the dial. So if we use it for the numbers that we used before, all right, just under 7 gallons a minute, 5 foot ahead, all right, we saw that the 007 was too big, that it was really close to the 006. So like I said, we get in between, just over the first dot, and now you've got the perfect size circulator for your application. And as our zones get smaller, we can see we can really dial it into where we need it to be. So I would say right here, we're going to have an 8-watt circulator, 9-watt circulator operating our house. Out here, we're going to be running, say, around 20 watts at that 7 gallons a minute, 5 foot ahead, 70,000 BTUs heating the house. So very versatile, because what's better than a 3-speed or a 4-speed circulator? Yes, that's right, an infinite speed circulator.
Dave, we've had a lot of questions come in, just involving some applications. Will these work well with an existing heating system, hot water and radiant? And the answer there is yeah, absolutely. It's any system you're using a standard efficiency circulator, and you can certainly apply an ECM circulator with similar, if not better, results, because you can dial in the speed that you're looking for, as you suggested. And again, especially with zone valves, it'll speed up and slow down as zone valves open and close based on the constant pressure mode that you've selected. One question was, I'm curious why you do 3 or 4 speed pumps instead of a variable speed on a potentiometer. And this question came up from Nicholas about I'd say about 30 seconds before you went into the 0018E. So I told Nicholas that was a brilliant question. So
that's right.
Nicholas, let us know if we address that appropriately for you, but that's a great way to run a zone pump system, because now you can dial it in to be exactly the speed that you need under design conditions. It's going to keep going that speed as it gets warmer out, so it will be over pumping. Right. That's one of the benefits, I think, of the Delta P or the Delta T VT2218 circulator, because that will change its speed not only based on zone valves opening and closing, but as a zone pump, it'll change its speed based on how cold it is outside to try to maintain that Delta T.
Right, exactly. So awesome. Thanks for the questions, everybody. Awesome. And I'm glad we got that brilliant question in there. The guy, he was reading the future. So yeah, that's awesome.
Kudos to Nicholas. Nice job.
All right. So what if you have zone valves? If you like to zone valve your systems out there, and we know when we do that math, we need a circulator to handle the flow when all zones are calling at the same time. We can't control when homeowners are going to need heat in the house itself, so we need to be able to supply a large enough circulator to handle all of them at the same time, which then it ends up being way too large for 80% of the winter, especially when we're looking at some of the more common zones that are going to be running in the house. So if you're looking at zone valves, we want that circulator to be variable speed and to maintain a constant discharge pressure. So what we have here is a couple of selections. Now this is showing an older dial of the circulator, all right, where we show the 5, 10, and 15 foot of head, all right, that the system needs. We actually have eliminated the 5 foot, and we just have the 10 and 15 available by the dial. But we have options to get to the 5 if you wanted to in the 18E circulator. So where do we set it? Well, it's going to be based upon the pressure drop that you have in the system itself. And we actually have this printed on the side of the box. If you're looking at your highest head zone or your longest zone at 85 feet of total length, meaning pipe from the circulator out to the house, count the baseboard, and then up to the suction side. If that was 85 feet, you're going to be around 5 foot ahead. If you're around 165 foot ahead, we're going to 65 feet in length, we're going to be around 10 foot ahead. And if you're heating the neighbor's house, we're going to need about 15 foot ahead. 250 feet of pipe. I'm not saying is impossible, but that's a really long loop length. Okay, so, but if you've got it, if you're over 165 feet, but under 250, then you're going to set this circulator at 15 foot of head, constant pressure. And we come ahead and take a look at the curves that we see here. And the blue line represents the full speed of the circulator if it was able to operate at the max on blue, all right, in that zone pump application. Now the orange lines, the solid orange is representative of the 5, 10, and 15 foot ahead mark. So if I were to turn this dial to the 5 foot mark, it would operate on this part of the blue line and then this part of the orange. The top part of the circulator is gone. So we're going to minimize the amount of over pumping that the system would do. So as we follow our application that we were looking at, it's at 7 gallons a minute. If this was a zone valve system, this is my 2 zones running, it'll operate out here. A zone valve closes and it bops back down to here. So this would be our full speed mode of everything that we need. And instead of it running full speed 44 watts way out here, we're actually really close to our design. And we're running, say, around 30 watts. Zone valve closes, we come all the way down to here. So in zone valve mode, it's going to bop back and forth on the horizontal, all right, and disregard this part of the circulator. You put it on 10 foot ahead and we're operating up here. Yes, we're going to overpump based upon our designs today, okay, but we're still full speed, 44 watts, all my zones running. I'll run out here and then it'll drop back to here as my zone valves open and close, okay? So I hope that makes sense. I do see a question from John coming in. Do those pressure drop calculations relate to copper pipe or PEX? Typically, those are your safe, trouble-free copper numbers. PEX, they'll be a little bit lower, all right? And you would have to take a look at some of your PEX manufacturers to get the more accurate numbers there. So when we come to your third mode of operation of your circulator is looking at thermostatic radiator valves and panel radiators being used throughout the house. And when you look at a TRV, these things are never fully opened and never fully closed. They're always modulating, and they're slowly modulating. All right, this little temperature head on top here needs to see a temperature change over a 90-minute span before it says, oh, I should start opening or I should start closing. So the temperature needs to change around that for over 90 minutes before it starts to open or starts to close. And in a thermostatic radiator valve and panel rad system, every radiator is going to have that TRV mounted on it. And so now you have a dozen of these, a half dozen of these in your home, and they're all at different positions, and therefore the flow is changing. Another application or another term that we might use for this would be, say, constant circulation, meaning the circulator continuously runs the entire winter because these TRVs are always just putting in just a small amount of heat into your space. If you remember from previous classes, these are typically operated on a 30 or 40 degree delta T across our system. So our flows are relatively low and we end up with a little bit higher of the head as our flow starts to increase. So we have plenty of these. And if we take a look at the inside of a TRV, and this plunger that comes down on top of here, you can see how the flow is changing and how it's modulating. It's not an open close type of actuator itself. We do have this cone and small passageways on the inside. So what we have now is a sliding position up and down, and need to know what your highest head is, what is your flow rate, and you need to pick the right curve. So if you all of a sudden say, oh yeah, 7 gallons a minute, 5 foot ahead, well, I'm going to set it on low and I'm going to slide up and down on this curve here, remembering that this is not for zone valves. This mode is used for your proportional valves, your TRVs, because our smaller zone actually had the highest head, so we would actually be starving it. Now it's so close based upon this picture here, but you see what I'm talking about. All right, that we need to make sure that we size this for the proper application. This is not designed for zone valves. Would it change speeds? Sure, it would. All right, but we have the option of doing the constant pressure mode for your zone valve applications. With that being said, one of the things that we also see on these quote unquote smart pumps out there, and we also have it on the 18E, is an option to put it in the active adapt, or the automatically figure out what you need button mode. All right. Like I said earlier, these circulators are not that smart. They're not going to do the thinking for you. And in some of these circulators that do have that, learning mode based in it, it is designed for your TRVs, or your proportional pressure curves. And what it's going to do is learn which one of these curves to operate on. And it slides up and down and may even change those curves. So for example, if your design point, your operating point starts to slide up towards the maximum line, it says, all right, well, I'm getting towards the end here, I'm going to have to jump up a curve. Now in the learning circulators, they have more than just these 3 curves. Ours has 9. So it'll jump up to the next one and then slide down. It's all about trying to use the least amount of power to move the most amount of water out to your system. So, and if it starts to slide down this end of the curve towards the left-hand side of your performance curve, then it drops down a line and then it slides back up again. So we're looking at this sliding up and down as your TRVs are modulating all over the place. But remember, it's got to take a long time to start figuring out what's going on. All right, so just remember, it's not designed for zone valves. The automatic modes, the learning modes, not designed for zone valves. All right, you need to have those proportional style valves or proportional flow designs in your systems in order to take advantage of that mode. I hope that makes sense.
Yeah, I think the important message here, which you said very well, is this isn't magic, right? Auto adapt, active adapt, they're not magic. It's not like you press the button, get the hell out of the way, and let the pump figure it out for itself, and you don't have to do anything. It's a nice story. It sounds really good, but it's nonsense. That's not how it works.
Right.
A lot of people have
It'll
said, well,
vary speed. Oh, definitely. Even if you hit that
absolutely.
auto mode with zone valves, you'll see the circulator opening, speeding up and slowing down, but it's not doing that we think it's going to do. Exactly right.
And if it's a system where the pump actually shuts off, all right, when the pump comes back on again, it'll do one of two things. It'll either go back to where it was the last time and have to start the learning process all over again, or to go back to its original programming and start the learning process all over again. So please understand, it's designed for continuous circulation, continuous run, for modulating thermostatic radiator valve systems. And it takes a long time to change too. It's like we need to see a certain drop in flow or certain change in flow for at least an hour before it's going to decide to change a performance curve. So again, it's a nice story. Hey, press the button. I don't have to do a thing. This thing's smart, figures it out. I am relieved of the responsibility of pump sizing. It's just not how it works.
Right. Yep. Excellent. All right. Keep those questions and comments coming in, everybody, because we're not done yet, but we are reaching the end. Okay. And the last thing that we can do in comparing your ECM and standard efficiency circulators out there is what makes these things die early. So what kills a PSC circulator prematurely, other than a long life? The lifespan of a standard PSC circulator, I talked to the engineers at the design engineers back at TACO, and they give us the numbers of 250,000 cycles is what we design our circulators to last to. All right, which equates to 18 years in a single zone, single pump system. So we can get a nice long life. However, circulators do die premature deaths every once in a while. And the most common ways is typically 2 of them on what's going to kill a circulator prematurely. All right. The first way is by getting a system airbound. A circulator that is airbound is not going to move any water around. It is also, these are wet rotor lubricated circulators, meaning the water that we're pumping is also lubricating and cooling down the bearing. So if we have air in there, you'll know it on the bearings because you're going to burn them out. You'll know it because you'll hear it squealing from the neighbor's house as you get there, as something's going on in there. So that's one big thing we hate in our circulators, having any air in our circulators. So that will kill a circulator relatively quickly. The second way that's going to kill our circulators is dirty water. Okay. I'm sorry if that, I know it's getting close to lunchtime for a lot of people here. So, but consider it a mojito instead. Yes, that's just the dirty water. These things, circulators do not like dirty water. Again, it's going to seize things up. And the most common time that we see dirty water or seized circulators, meaning the impeller's not moving any longer. We see that in the fall when we have systems sitting around and the tolerances between your impellers and the cast iron are really, really close, very close tolerances that we have in there. So if you get a little bit of rust buildup on here in the summertime as it's sitting around, when the winter comes along and the heat kicks on, it's holding that impeller in place. So, and what ends up happening is that the motor starts to get really, really hot. The green paint on them starts to turn brown a little bit, and then eventually, boom, the motor's done. All right. So those are the two things that are typically going to prematurely kill a circulator. Now, we know this because we analyze tons of circulators that come back to us over time. And just because we want to look into it ourselves, we have a lab back at the factory. And if you've ever been in Rhode Island, if you ever want to come and take a look at it, you want to see how we kill circulators on purpose, it's fun. I wish I had, if I didn't have this job where I didn't get to hang out with these two guys all the time, Rick and John, that's the job I wanted. Sorry, John. I would work in R&D where I get to break stuff on purpose, all right, and come up with creative ways to do that. I would love doing that job. So when it comes to the ECM versions, we wanted to try to eliminate these two things. So it's a feature that we call SureStart, and SureStart is an automatic correction feature. It's nothing that you can do into the circulator to make it happen. It does it all on its own. So it has a locked rotor feature. So if the impeller is not spinning, the circulator actually stops. All right. The white flashes from white to red, and then it shakes it back and forth, trying to break it free. And then it goes up to full speed. It knows the impeller's not turning, and it stops it. It shakes it back and forth, and then it goes to full speed, full out, around 4,800 RPM. It's trying to, regardless of where the dial is set, it's going to try to break it free. If it doesn't up at that high speed, it stops, shakes it back and forth again, goes back up to that 4,800 RPM. That's going to happen about 100 times in 20 minutes in doing that locked rotor. If it doesn't free itself in that 20-minute time period, the light turns solid red and the circulator shuts off, saying, something's preventing me from turning. I'm not going to stay running here and burn out. Somebody needs to figure out what's going on, either take the circulator apart and take whatever's holding it in place or clean it out. So that's your part one of your SureStart. The second part of SureStart is if it is airbound, meaning that we're not purging your system, meaning that we get air stuck in the casing in the impeller here itself. We need to get that air out because these things do not pump air. All right, we need to get that air out of here. So what it does is it does a quick drop in speed. You'll get a single flash of light, quick drop in speed to try to move the air bubble out of here and into the system itself to eventually bring it back to your air elimination to get the air out that way. So that's just going to a quick drop in speed, quick white flash. And we see that a lot when the circulator kicks on for the very first time. You're going to see these flashes of lights, and it may make that little bit of noise and be a little disconcerting in the beginning because, hey, my standard PSCs never did that before. This is doing stuff on purpose and trying to get those air bubbles out of there. Like I said, you don't make it happen. It does it all on its own to give you a longer lifespan out of these circulators to prevent the premature failures of circulators that are running out there based upon system conditions and water conditions that are out there. So that actually ends the class. And John, holy crow, I finished 1 minute early, man.
Good
that
job.
Almost never happens.
Good job, dude. Good job. Nicely done. Nicely done.
I was getting a little nervous there, thinking I might run a couple of minutes over. So Please type in any questions that you may have while you're out there, everybody. Greatly appreciate them. We will stay online as long as need to cover off on all those questions. But before we do, I want to make sure that next week's class, all right, that everybody that wants to come and hang out, is a deep dive into the FI and CI circulators, the big pumps. We're switching next week over to a commercial focus. So Rich and Brett will be running the show and going over a deep dive in how the FI and the CI circulators operate, and all the other jazz. I may actually have to go myself because as John and I and Rick normally talk about, when we do training classes, people ask us what we can do. Well, if I can carry it in one hand, I can do training on it. I know an FI and CI pulls water in one side and out the other, and that's about as much as I know.
There you go.
So,
hey, Dave, I got to tell you, we had another brilliant question from Rick W. down in New Orleans, who asked about heavy calcium when you're talking about things that kill pumps. We have plenty of that here in New Orleans, and I would say a nanosecond after he typed in that question, you started talking about SureStart. So excellent. Rick did have a follow-up question about how long does it take to set that up. In fact, the setup time for SureStart and for SureStart it is nothing. It's built in, so it does that automatically. You don't have to do anything when you're installing the circulator to do that, Rick. When you're using like our 006 E3, which is our ECM domestic hot water recirculation pump, all you need to do is select the speed. It goes back to like that potentiometer that we were talking about earlier, although technically it's not a potentiometer. It's just a speed selection, and you select the speed that you want that circulator to run at, and that's the speed the circulator will run at. So once you just determine what that should be, and we have an app that can help you do that too, and the app will take you maybe 5 minutes if you dawdle to figure out what you need and where to set it up. But that's about it. In terms of setting up SureStart or anything like that, it takes no time at all. And if you use our smart plug as a control for your domestic hot water recirculation, there's actually no setup time there either. It's a plug that plugs into the wall socket, and then you plug the circulator's line cord into the smart plug, strap on a sensor, and away you go. It learns the domestic hot water usage for that home, and it'll repeat their usage patterns and constantly relearn. So in terms of setup time, there's not much there. So
I just saw a question just drop in from Vincent, and he was asking about SureStart on all of the ECM circulators, our smaller circs, not up to the VR versions. So right now, our ECM circulator lineup goes up to, I believe, 65 foot ahead, 320 gallons a minute. So some of the big pumps, they do not have SureStart built in. Our smaller ones do. So from the 18 down, and Rick, maybe you can correct me, I'm not sure on the 26 and 34 models, if we have SureStart built into those.
Yeah, up to 170 watts.
Okay.
Yeah,
excellent.
170 watts has got SureStart built in there.
Excellent, excellent. Yeah, so I want to go back a little bit here where, again, we talked about why using ease of balancing and matching the load for ECM circulators. And again, when we're talking about smart pumps, got to understand the limitations of smart here. I can remember, and I'm not sure if this is what the person who made the comment meant, so I just understand that. But I can remember having discussions previously about why people use ECM circulators, and one person said it means I don't have to balance it. It does all that automatically. And we were talking about a radiant system, and we were talking about using a manifold to feed different zones. And ECM circulators, variable speed circulators, don't do that. They don't. If you got a long loop and a short loop, all right, and both are open, I don't care what pump you have, anybody's pump on the planet, the short loop's going to get the flow till the short loop's happy, then it'll close, then the long loop's going to get its flow. That doesn't change regardless, because they may be variable speed circulators, but they can only run one speed at a time. So we're not going to get that automatic balancing again, I'm not sure the questioner meant that. I don't think he did, but I just want to make sure that loop was closed, pardon the pun.
Hey,
and then
John, one thing they might have meant, because I think that's what was misinterpreted a long time ago when they first started saying that these were self-balancing, is they're talking about the initial balance of the system circulator and trying to get it to run back up in a more efficient area of the curve, which was done by artificial resistance, with a triple duty valve or something like that. In that sense, the pump is self-balancing
Yes,
because
yes.
it turns itself up and down, and you don't need to add that artificial resistance. And that might, I'm just throwing it out there because that might be what they were referring to.
Sure, sure. And that makes a ton of sense. Yeah. And then the other one was matching the load. Again, depends on the circulator. If you were to set up a delta P circulator like our 0018E in a constant pressure setting for zone valves, if you pick let's say the 8-foot ahead line or the 10-foot ahead line, that's the line it's going to run at. It's going to run at a constant pressure of 10 foot ahead, and as a result, those the zones are going to get the same flow in October as they do in January as they do in April, because you have to run on a performance curve. And once you set a constant pressure at 10 foot ahead, that's the performance curve it's going to run at. Now the speed will vary, the electrical consumption will vary, but that performance line, that flow and head will remain consistent as zones open and close no matter what time of year. The benefit of the VT2218, the Delta T pump, is depending upon the size of the system, for a nice chunk of the heating season, the speed will vary not only with zones opening and closing, but also with the outdoor temperatures. We try to maintain a 20-degree Delta T, or the Delta T that you have designed the system for. So there's a little bit of variation there. And again, the Delta T pump is really maybe the most efficient way to run a variable speed circulator, both electrically and making the system overall as efficient as it possibly could be. And there was one other question about capital costs and quote unquote payback, in terms of the additional costs of these circulators compared to how much electricity they'll save. Again, that's kind of depends. Is it if you do the math, if you work the math out, could it be 2 years? Could it be 5 years? Just on electricity? Yeah, I'm sure it's somewhere in there. It depends on your cost per kilowatt hour. Obviously, the higher that, and it depends on the horsepower of the pump too. The bigger the pump, the quicker the payback. Or offset is a better word. I hate the word payback, but because the only way these things will pay you back is if they get a part-time job, but in terms of overall efficiency, the closer one of the things variable speed circulators do for us is they allow us to get the performance curve closer to reality than, say, a fixed speed circulator would. So if you really do the math and know your flow and head, you have the ability to get the performance of a variable speed circulator closer and closer and closer to that, which to me is going to limit short cycling throughout the heating season. And when you limit, if you have a boiler that's not short cycling, you have a boiler that's going to be more efficient, right? Because a short cycling boiler is not an efficient boiler. If we can limit the number of cycles, maybe the runtime is going to be the same, but we do it in fewer cycles. Now we can enhance the overall efficiency of the entirety of the system, which is really the big benefit of variable speed.
Well, that was excellent.
I left you in awe there, didn't I?
Yeah. Yep. Definitely. So, excellent explanation, JB, and excellent questions coming in from the crew out there. So greatly appreciate all that. I do greatly appreciate everybody joining us for Takeo Tuesday, and I hope these are helpful to you all. That you get some information out of them, that you're learning some stuff, having some fun, and stuff like that. So we have a lot of fun doing these things too. And they're not going away. They're not going away. You guys have a thirst for them, and we'll keep doing them.
Can we be added to? Can I add you one? There's one more question that just came up. I saw Rick answered it, but I think it was worth addressing. Where Vincent asked about, is it ideal to keep the loops relatively similar in length and head in a radiant system? No, not really. It's got because radiant manifolds have balancing valves on them, and you know they're not really designed to dial in an exact flow rate. Really, what they're and I don't care what the flow meters say on them because they look pretty, but they all do basically the same thing. Is that they're designed to they're designed to trick the water into thinking all the loops are the same length. All right. So if you use those you know a manifold that has the balancing valves on it, you're going to balance right there anyway, and you're going to trick the water into thinking all the loops are the same length. So you don't necessarily have to design to keep the loops the same length if you have balancing manifolds. It saves a lot of time and can save a lot of pipe too, because I can remember a guy with non-balancing, he just made his own headers out of copper, and to keep his loops relatively the same length, he coiled up about 60 feet of pipe and kind of hung in a wall cavity just so the loops would come out to be the same length. The homeowner, I could say, why the hell is this wall so hot? You know?
Yeah, right.
You know, but those are the lengths you'd have to go through, and it doesn't make any sense to do that.
Excellent.
All righty. Great class, Dave. Excellent job, and thank you to all for your great comments and everything. And we'll see you in 2 weeks on Takeo Tuesday.
Excellent. Thank you very much, everybody. Have a great rest of your day and a great rest of your week. Takeo After Dark for my residential people and anybody else that wants to come and join. Takeo After Dark tonight, 9 p.m. Pacific, 9 p.m. Eastern, or 6 o'clock Pacific time. And tomorrow night, so tonight would be part 3, tomorrow night part 4, 7 o'clock Eastern. So takeotraining.com/training. Take a look if you're interested in coming to hang out with Takeo After Dark and the boys. So we'll be there. It'll be fun. Catch you all later. Enjoy.
Oh, and I have to answer Jerry McPeak's question. He was asking about Speed Racer, and I said it's the second greatest cartoon of all time. And he just asked what was the #1 cartoon of all time. Bugs Bunny, Daffy Duck, Rabbit Season, Duck Season. That's all I have to say. That's all I have to say.
Yes. I'll have to agree there. Yes.
Which is kind of like a typical conversation between Rick, Dave, and I. It's Rabbit Season, Duck Season, you know.
Nothing ever gets done. Yes.
No. Take care, everybody.
Enjoy, y'all.